Now I'm going to start to talk about the 3D equilibrium. If we have an object in 3D space and how we are going to find out if the forces are in balance and make sure that if the object is at rest, it's going to stay in rest. It's very similar to 2D. We just need to make sure that if we have forces, we make sure if we add all the forces in the vector format, they become zero. So in other words, all the forces in 3D cancel each other. If you remember in the 2D, when we were working, we mostly prefer not to work with a vector. So we find the component of each forces at the x and y direction, and then we said, okay, all the forces in the x direction should cancel each other, all the forces in the y direction should cancel each other. It is true, but it's not in the 3D, but it's not as easy to do that in 3D as it was in 2D. Most of the time, it's not very convenient to find the component of each forces on the x, y, and z direction. If it is, sometimes it is, that's okay. But if it is not, we need to, instead of working with a scalar and finding component on x, y, y, z, we need to work with Cartesian method, as we speak about that before. So if we have the 3D forces like that, and we want to make sure that they cancel each other, eventually what we have is that we have sigma f x I plus sigma f y j plus sigma f z k is 0. In other words, we make sure sigma f x is 0, sigma f y is 0, and sigma f z is 0. That's what we want to work on that. But before we get to this point, because we can't find that, we need to go to the Cartesian method to write the sigma f in this format. And if you remember, when we were talking about the position vector, we talk about how to find the forces along a line, or vector along a line. I'm going to just review that one more time. So if we have a force or any vector, we can write that vector as its magnitude multiplied by its unit vector. And the unit vector, it says that it is the position vector divided by the magnitude of the position vector. And the position vector between 2 points A and B is xb minus xa I plus yb minus ya j plus zb minus za k, and the same is magnitude is just xb minus xa squared plus yb minus ya squared plus zb minus za squared. So it's the magnitude of any position vector going from point A to point B. So if I have the point A, it has a xa, ya, za, and point B with the coordinate xb, yb, zb. So when we are working with 3D forces, this is how we are going to find each of the forces in the Cartesian format. How to do that? We'll find the position vector that along a line, that force apply on that line, that it has a line of action of that force. So we find a line that, assume the line that force apply along that line is AB. So we find the position vector and its magnitude for that line. Then we find the unit vector for that line, and then we find forces along that line. So we can do that. So if I want to make sure, so if I have a force along line AB, so it's the force, it's magnitude of force along line AB, and the unit vector along line AB. So it's AB, so it's AB, so it's AB. And what it says is if I have a force, for example, if I have a point A and I have a point B, like that, and then I have a force along that line, so I have a point A, point B, and force along that line. This is how I'm gonna find the vector FB. So the vector F along AB is its magnitude times its unit vector along, and the unit vector of the line AB is the position vector of line AB divided by the magnitude of the position vector, and the position vector of line AB is calculated from here. The magnitude of that position vector from line AB along line AB is calculated here or here. So basically we go backward. So we calculate these two first, then we calculate this one, and then we calculate the force. And after we have all the forces calculated in the Cartesian method, we just add them all together and make them equal to 0, and by then we get we can write these three equations, and then we solve these three equations for any unknown that the problem gives us. So you remember when we were talking about the 2D equilibrium, there was a step to solve the problem, and this step was draw the free body diagram and then put all the external forces on that free body diagram. Find the exponent of find the component of all the forces on the x and y axis, and then add all the component along x-axis together and add all the component along y-axis together. The same thing we are doing in the 3D, a little bit the same thing we are doing in 3D, but a little bit different. So again, what we are doing is we draw the free body diagram. We put all the forces on that. So assume, I'm going to just give you very simple. So assume this is the y, this is the x, and this is the z. And let's assume there are a couple of forces applying on that. So we put all the external forces applying on this one. For example, so draw the free body diagram, put all the external forces on that diagram, then write all the forces in Cartesian format as a like that. F1 is F1xi plus F2 plus F1j plus F1yj plus F1 in the z direction k. And the same, we write it for all of them. So it's the F1, so it's the same thing for the F2, F2i plus F2j plus F2k. And the same for the, for example, here for the F3, as we have, assume we have three forces. So F3i plus F3 plus F3. And remember, as I said, the forces, any forces is just its magnitude times its unit vector. So we can calculate that, and from there we can get these equations. Assume, for example, like that. After we have all the forces written in the Cartesian format, we are gonna write that sigma fx in the vector form equal to 0. So the same thing here, if what it means that I'm going to add f1 plus f2 plus f3 equal to 0. So sigma f equal to 0 is going to be f1 equal to 0, so it's going to be f1xi plus f1yj plus f1 zk plus 2xi plus 2yj plus 2zk plus 3xi plus f3yj plus f3zk. So it's this one also is z. So I have this is going to be 0. Now I add all the I component together, all the j component and all the z component together. So it's going to be sigma f is going to be all the all the I components. So it's going to be f1x plus f2x plus f3x I plus 1y plus f2y plus f3y j. So all the I component together, all the j component together, all the z component together, fyz plus f2z plus f3z k. So I add all the three and it's 0. Now if I look at them, this part, all the component all the I component, this is sigma fx. All the y component is sigma fy, and all the z component is sigma fz. So all I need to do to solve this, I'm gonna write that here, the three component of them. So it's going to be sigma fx is 0. It's going to be f1x plus f2x plus f3x is 0. Sigma fy is equal to 0, which is the component of j, all the components of j is f1y plus f2y plus f3y is 0, and all the z component is 0. So it basically all the component of the k, all the k components got to be 0. So f1 is z plus f2 is z plus f3 is z is equal to 0. So it gives you 3 equation, 3 unknown, and you can solve it to get all the values you want. So remember, that's the procedure that we use to do that. It doesn't matter how many forces we have 2 forces, 3 forces, 4 forces, that's all the same thing. Draw the free body diagram, draw all the forces, find the Cartesian forces, Cartesian format of all forces like that. Then add all the forces in the vector format together. Put all the I component together, put all the j component together, put all the k component together. Then all the I component is your sigma fx, make it equal to 0. All the j component is your sigma fy, make it equal to 0. And all the k component are your fz, make it equal to 0. Gives you the system of equations, sets of equation, and you can solve it to get any unknown you have in your problem. Okay, now let's look at an example for 3D equilibrium and how we are going to solve the problem in that case. Here, assume that I have a box of 100 Newton, which is connected with a cable to the ring O, and that ring is held in a place with 3 cables, which is OC, OA, and OB. So these 3 in the 3D space hold this box in its place. I want to find out forces that go FOA, FOB, and FOC. We want to find these 3 forces. We want to find the 3 forces that actually hold that box in a place. before we start, we know that when we have this problem like that, one thing that we may need, we for sure need, because is the position of all points, because as I said, we need to calculate the position vector. So it's most of the time it's convenient, before you start to do any calculation, just find the coordinate of the points you need. So here the coordinate of the points I need, I'm going to put the point A. The coordinate of the point A, if you look at the example, is at 1, -2, and 2. And for point B is -1, -1, and 2. And for point C, we know that it has a 0x, 0y, 0z, and we don't know how much is a y value. So these are the coordinate of this one. Again, for example, for the A, it has a 1 along the x, it has a -2 along the y, and has a 2 along the z. The same here for the B, it has a -1 along the x, it has a -1 along the y, and has a coordinate of 2 along the z. And the z is sitting on the y-axis, so x and z is 0, and we don't know where exactly it's sitting there. So we want to start to find those three forces. The very first thing that we need to find out is that the position vector for OA and OB. And if you remember, the position vector for OA is and the O is at 0, 0, 0. So the XA minus X minus XO, YA minus YO, and ZA minus ZO. So it's going to be, I'll just write for the A, so it's going to 1 minus 0I plus -2 minus 0J plus 2 minus 0K, which is simple, just is 1I minus 2J plus 2K. The same for OB. So it's -1 minus 0I and -1 minus 0J plus 2 minus 0K, which is going to give us -1I minus 1J plus 2K. And if you are comfortable with doing it, you can just skip this step and directly write that part from the beginning. So these are the position vector along that OA and OB. And also we know that if we square all the component and take the square root of that, add them together and take a square root, is the magnitude. So I'm going to skip that part. So the next thing I need is the unit vector. So I have the position vector, that was the first part. Then I need the unit vector for either of these two. So I'm going to write the unit vector here. For OA, the unit vector is the position vector divided by its magnitude. So its position vector is 1I plus, minus 2J minus 2J plus 2K. So it's 2K. And divided by its magnitude is 1 squared plus -2 squared plus 2 squared. So this is the unit vector along OA. And if you do the calculation, the unit vector OA comes out at 0.333I minus 0.666J and plus sorry, 0.667. J and plus 0.667 K. So that's the unit vector along the OA. And we need also the unit vector along the OB, which is similarly is the position vector along OB divided by its magnitude along magnitude of the position vector. The position vector is negative 1I minus 1J plus 2K, and its magnitude is just square all the component, add them together, and take the square root of that. So that's the, so if you do the calculation, this comes out at as negative 0.408 I, negative 0.408 J, and plus 0.816 K. So that was as the so this is let me draw that again. So that's the position vector for the OA, and that's position vector for the OA, position vector for the OB, the unit vector for the OA, the unit vector for the OB, and then we, by knowing that, we can start to find forces that we have. So the forces that we have, we have 4 forces here, if I want to say apply on that. So let's go back and okay. Remember when we're talking about the 2D equilibrium, the step was like that. You draw the free body diagram, put the external force, all the external forces on that, find the component of forces on the x and y direction, and then write the sigma of x equal to 0, write the sigma of y equal to 0. We are following the very same procedure here. When we are working with 3D problems, so we draw the free body diagram, we put all the forces on them. Then here, instead of finding the component of them, we find the forces in Cartesian method in 3D. We find all the forces in 3D, and then we add all these vector forces together and make them equal to 0. So one more time, when we are talking about the 3D, this is how we are going to do that. So we add all the forces together, we draw the free body diagram, we draw all the forces, external forces act on that free body diagram. We find all the forces in 3D Cartesian format, and then we add all the forces together. So here the same thing, I'm going to do that. So I'm going to just draw x and y and z. So it's going to be x, sorry, y, z, and it's x. So it's x, y, and z. And if I have the ring sitting here, I know that the weight is applied on that external forces. One of them is the weight of the box. The other one is the force of OC. The other one is force at OA. And the other one is the force at OB. So I start with W and OC because these two are easier. The W, if I'm going to write that, the W, if I want to write it in Cartesian method, very simple. It doesn't have any X component, it doesn't have any Y component, it only has Z component. So it's going to be just W minus WK. So that's the forces, if I want to consider that, which is going to be minus 100 Newton K, because it only has the K component, it doesn't have a X, Y, and Z. The same for FOC. If I look at the FOC, because it's along the y-axis, it doesn't have a z and x component. Again, it's very easy to find that the Cartesian format of that is going to be its magnitude on the positive of y direction. So it's going to be J. So these are the two forces I have. So these two forces, because they're along the z and y axis, very easy to write them. For the FOA and FOB, it's not that easy because they are 3D, they're not along any axis. And if you remember, we have to use the positional vector to write them. So I go back there and show how to write them. We have, for example, for OA, we know that the is its magnitude times the unit vector of that. So its magnitude, which is what we want to find, and the unit vector of OA is 0.33 I minus 0.66 J plus 0.66 K. So I only keep two numbers after the point. The same here for FOB. So I can write for FOB, and I can multiply it by that, so we get the correct value. So the same also for FOB. So we have the FOB is equal to the vector of that is equal to FOB and the unit vector of OB, which is going to give us FOB, the magnitude, which is what we look for, and the unit vector for FOB, which is this one, negative 0.48 I, 0.48 J, 816 K. So these are the other two forces I have. So the W and FOC, the two forces that are along the axis, so we can write it very easily, and the other two forces, which are the 3D forces, which we use the unit vector to write them. Now we have all the forces. All we need to do is just to write the sigma F equal to 0. That's all we need to do to solve this problem, to write the sigma F equal to 0. So before I write that, so I'm going to write these two equations down here, so we have them on the board, and I write the equation. So the same here, FOA is its magnitude, FOA 0.33 I minus 0.66 J plus 0.66 K, and FOB is FOB its magnitude minus 408 I minus 408 J and plus 816.816 K. So these are the other two. So these are all forces that we need. And now we're going to write this equation to solve our problem. So we want to write the sigma F equal to 0. So I'm going to start to write all the forces I have. So it's going to be FOA plus FOB plus FOC plus W should be 0. So I'm going to write this. So FOA is its magnitude times 0.33 I minus 0.66J plus 0.66K. So this is the FOA, and plus FOB minus 408I minus 408K plus 816J, and plus FOC, which is going to be FOCJ, and plus W, which is negative 100 or minus 100K. So if I add them together, this is what I'm gonna get. So it's gonna be equal to FOA, FOB, FOC, and W. So add all these forces together, this is what I'm gonna get. Now, when I got to this point, I'm gonna add all the I component together, which are the component along the X, add all the J component together, which are the component along the Y, and all the K component, which are the component along the Z direction together. So to get the draw the line here. So I write sigma fx equal to 0. So I add all the Y component together. So if I want to, it's basically, it means that I component is sigma I component is 0. So I'll add all the I component together. So it's gonna be the sigma fx is 0. It means that I'm gonna have 0.33 FOA minus 0.48 FOB is 0. The same for sigma Fy. For sigma Fy equal to 0, I write all the J component together. So I add all the J component together. So if I add all the J components, I got minus 0.66 FOA minus 408 FOB and plus FOC equal to 0. And the same if I write the sigma Fz equal to 0. To get that, I add all the J component together. So all the J component I have here, I just add them together, and it's gonna give me 0.66 FOA plus 0.816 FOB minus 100 is equal to 0. So if we look at here, we have 3 equations, 3 unknown. So we can solve these sets of equations simultaneously and get the FOA is comes out 70.5.01 Newton, FOB comes out 61.22 Newton, and FOC would be 75.01 Newton. So if I go and do the overview over what we have done, is that when we have the 3D problems, we need to find all the forces in Cartesian method. So we draw the free body diagram, put all the forces there, and we try to find all the forces in Cartesian method. And after we have all the forces in Cartesian method, we just add them together in a vector format and make it equal to 0. So if we have forces sitting along the X and Y or Z axis, it's very easy to find their Cartesian method because they have only one component. If they are not sitting along X, Y, or Z component, and there are actually 3D forces, we have to find a position vector along that force. Then we find the unit vector along that force, and then write the forces based on its unit vector. After we have all forces written in the Cartesian format, then we write a sigma f equal to 0. We add all of them together in a Cartesian format. Then we'll get sigma fx, sigma fy, and sigma fz equal to 0. The sigma fx is simply add all the I components together. The sigma fy is just add all the j component together, and sigma fz is just add all the k component together. It gives you the sets of equation, and then you can use those sets of equation to solve for any unknown you have in a problem.